We have described how electricity, magnetism, and motion are all interconnected. So let us apply these principles in some cases we encounter in our everyday lives. This slide shows you the setup of an electric motor. So when you attach a battery to the ends of the motor rotates. How does this happen? In this case, you see that the coil is placed in between the ends, the north and south poles of a magnet. And so there are field lines going from the north to the south, in this case towards the right side. And when you attach a battery to it, there is a current flowing. The direction of the current is shown at one instant. On the left segment of the coil, the current is going upward, and in the right segment, the current is going downward. Now let us apply the equation we looked at before. The electromagnetic force F equals QV crossed into B, right? So the direction of the positive charges flowing is along the direction of the current in this case. So I'll apply the right hand rule again, my thumb pointing upwards, and then I crossed into the B. The B field is towards the right, and I see that there is a downward force like into the page in this case, acting on the left side of the motor. Similarly, on the right side of the motor, because the current is flowing in the other direction downwards, the direction of the force is reversed. Basically, the force is now pointing out of the page. So on the left side, the force is pointing into the page, and on the right side, the force is pointing out of the page. So these two forces are actually exerting a torque on the loop, and this torque causes it to rotate basically. Now once it has rotated through 180 degrees, then the currents are reversed in the in the left and the right side. So actually the polarity of the voltage needs to be reversed also. So this means if you apply a DC current after an 180 degree rotation, you have to change the polarity of the DC current between the terminals. Or if you are already using an AC current, then this happens automatically. So basically you need this for the motor to rotate continuously basically. In this case, basically this is the principle behind most of the electric motors basically. So you have magnetism from a permanent magnet, you have electricity, the current flowing in the coil, and this generates a motion, a rotational motion in this case, which you can use to do some work basically. So now let us look at the reverse situation. This is a generator. So you have a permanent magnet again with the north and south poles creating a magnetic field. And in this case, you have to generate electricity out of it. So that means you have to get a current out of it, or an electromotive force out of it. How does a generator work? So you can think of a windmill. Windmill is a generator, for example. The wind flows and rotates the fan of the windmill, and this fan is actually connected to a coil like this. And when the fan rotates, the coil also rotates. So there is motion, rotational motion already coming from the wind energy. Now we know, like if there is a B field and there is an area, in this case the closed loop has an area A, and we have seen that the magnetic flux actually depends on the dot product between the magnetic field and this area. So in this case, because the area is changing, it's rotating, the angle between the B field and this aerial vector is changing. So the B dot A, the product is changing, and this product is actually the magnetic flux. And we know when the magnetic flux changes, there is a potential difference that develops in the closed circuit basically. So there would be a EMF developed at the ends of the coil, plus and minus, and in this way you can create a current through the coil. So you have converted wind energy into electrical energy. Similarly, in the same manner, you can you can generate hydroelectricity. So water falling from a height can cause also this kind of rotation of a coil, and using the same principle, you can obtain electricity out of this setup. We have previously talked about DC currents. DC currents are called direct currents. They have constant direction and constant magnitude. Now let us look at alternating currents, where the direction and the magnitude of the current is changing periodically. So this is called alternating current, direction and magnitude changing in an alternating manner. And the current is shown in this plot here as a function of time. Uh, it can assume the form of a sinusoidal wave, such as this, and the current can change its direction, so it's going from plus to minus over some time period. It's also zero at some instant, and it assumes highest value at some other instance. And this shows the setup of an AC circuit, a circuit that operates with an alternating current. So you see the supply voltage here with some magnitude 100 volts. But to describe AC currents, we also have to specify their frequency, because this is a periodic current, right? So you need to know the period of the current. And in this case, it's shown to be 50 Hertz. And there are three components that are shown here in an AC circuit. You have the resistance, you have the capacitance. These two components we have already described in the context of DC circuits. But we see that there is a third component here, denoted by capital L. This is called an inductor. And we will see how the supply voltage gets distributed across these three components when there is an AC current flowing in the circuit. Let us look into the inductor in a little more detail. This is a new component. We haven't described this before. An inductor has something called inductance, just as a capacitor has capacitance. The symbol for an inductor or inductance is a capital L. It has the unit of Henry. Henry is also given by volt times seconds over amperes. So this equation on the right side, this shows the expression for the inductance. L equals N times delta phi over delta I. So change of flux and change of current. And N here is the number of turns. So a good example of an inductor is a solenoid, which is a coil. We have already looked at it. And when there is a current flowing through the coil, there is a magnetic field that develops through it. And so if there is an alternating current, then this magnetic field is also changing in time. So what an inductor describes the storage of magnetic field, basically. It stores energy in the form of a magnetic field. So if you have a DC current flowing through this wire, then there is no effect. It just acts like a resistor. But if there is an AC current flowing, then there is this additional effect that the energy of a magnetic field is stored in this type of component. So what are the features, some of the features of the AC circuits? The power source is now AC and alternating, so it changes polarity between the two terminals in time. So one terminal is positive for some time, and then after some time that terminal becomes negative. So it's alternating between positive and negative over some time. And so now let us look at the voltage relations. If you apply a AC power supply to a circuit, how is the voltage distributed across the three components that we have talked about? First, let us discuss the resistor. The important thing to note in an AC circuit is that we have to also think of the frequency. That is the period by which the AC current is changing. In a resistor, this frequency aspect doesn't come into play at all. So current is still given by Ohm's law in most of the materials. Resistance does not depend on frequency. So the resistance of a DC circuit and an AC circuit is the same. It's just the relationship of voltage over current. Now in general, so although resistance, the voltage drop across the resistance is the same, but in general for the other components, if you have an AC voltage source, then the voltage current relationship is a bit different. There is a new aspect that comes into play, new property called phase difference. That means if basically two waves can be out of phase, as we have seen in the module on waves. So in a resistor, current and voltage are always in phase. But when you have the other components such as capacitance or inductance, current and voltage may be out of phase actually. So this is one of the prime features of AC circuits, and this is how it differs from DC circuits basically. So there is a phase difference between voltage and current. In DC circuits, voltage and currents are always in phase. So if you have a supply current given by the sinusoid, I equals Im sine omega t, where omega is the angular frequency of the wave and Im is the peak amplitude of the current. The voltage drop across a component is given by, in general, by an expression something like this: V equals Vm sine omega t plus phi. So again, Vm is the peak voltage amplitude and omega is the angular frequency of the wave. But you have this additional term here, phi, which is the phase difference basically between the two waves. When the ratio of voltage to current does depend on frequency and there is a phase difference between the two, we call this the impedance. So what is the impedance? Impedance is V over I, but V and I are both AC currents and voltages now, and they have this the expression that we just showed. So this is called impedance as opposed to resistance. We have looked at resistance as simply V over I, the DC components, but now we talk about impedance, and there is a phase difference between the current and voltage. In the case where the voltage and current are out of phase by 90 degrees, it is called a reactance. Now this is to summarize the current voltage relationships between of the three components in an AC circuit. So first we show the resistor, and the resistance is defined in the same manner as for DC circuits. It's just voltage over current, and in this case voltage and currents are always in phase. For the capacitor, actually the voltage lags current by 90 degrees basically. In case of the capacitor, we talk about the reactance, and the V over I, the voltage drop across the capacitance divided by the current, is given as 1 over omega C. C is the capacitance and omega is the angular frequency of the current. And why is there a phase difference between voltage and current? Because you can think of the voltage drop across the capacitor. So as soon as the current is flowing, charges are building up. So the voltage is not instantly the supply voltage. It takes some time for the terminal of a capacitor to reach the supply voltage. So you can see that there is already a phase difference between current and voltage in this case. Now what about the inductor? So we talk about inductive reactance. So this is defined as VL over I, where VL is the voltage drop across the inductor, and this is denoted by X sub L, and this is given by omega times L. L is the inductance and omega is the frequency of the AC signal. And for an inductor, V leads I by 90 degrees. Also, this is also related because the I is changing in time. When the change in I is maximum, voltage change is actually not maximum, so there is actually a phase difference between current and the voltage.